Welcome to this video, and in this video I'm gonna explain the use of the bootstrapping method in claims reserving to come up with simulations, with draws from the predictive distribution of the outstanding reserve, the outstanding claim amount. So our basic setting is data aggregated in a so-called runoff triangle, and we're gonna work here in this video, in this example of the bootstrap. We're going to work with incremental claims data, which I can denote, for example, with xij, where the j runs over the accident years or the years of occurrence, and the j runs over the development years, right? So that's what we've discussed so far, what we've covered in earlier videos. And our goal is now to say something about what's going to happen in the future. So what is going to happen in this lower triangle. And a basic model to start with is then the over-dispersed Poisson model to structure, to model the random variables xij. So we're going to assume that the xij is from an ODP model, so an over-dispersed Poisson model, with a certain mean, say mu ij, and a dispersion parameter phi. So that implies that the expected value for our xij is given by the mu, typically structured as, say, the exponential of an alpha I parameter plus a beta j parameter, where the alpha I parameters capture trends in the direction of the occurrence years, and the beta j's cover trends or patterns in the development year direction. And then for the variance of this xij, because I've got this over-dispersed Poisson, that's phi times mu, okay, where I expect this phi to be above 1. Now the reason why I propose to start with this particular model is because then if you estimate the parameters alpha I, beta j, and if you estimate with a point estimate the outstanding claim amount in the future, in the red lower triangle that you see in this picture, you'll get exactly the same point estimate as the traditional chain ladder would lead you to, right? So we would estimate the parameters, for example, with maximum likelihood. So that would give us alpha hat I, beta hat j, and then we can get a point estimate for the outstanding claim amount, that is the amount that corresponds to this lower triangle for the future. Okay, so now we want to continue with this model, but instead of just getting a point estimate and perhaps also a measure for the corresponding standard error, we want to be able to come up with a predictive distribution for this outstanding claim amount, such that from this predictive distribution we could calculate any risk measure that we're interested in. So that's our goal. And in order to do so, we're going to introduce the so-called Pearson Residuals, which correspond with this Poisson model that we started with. Yeah. So the definition of a Pearson residual in this Poisson model would be that you get, say, Rpij being equal to my xij minus the mu ij divided by the square root of this mu ij. Now, of course, here in this notation, the xij is my observed amount in a cell in the upper triangle, and then the mu, that would be what I'm going to estimate for this cell in the upper triangle using the specifications that we introduced over here. So typically I'm going to denote this mu with a hat, and because that would be my estimate relying on the parameter estimates for alpha I and beta j. And so, as mentioned, this xij, that would be a particular cell over here. And I can do this for any cell in the upper triangle. Now, one thing to keep in mind here with these Pearson residuals is that they are easy to invert. And we're going to rely on this idea when setting up the bootstrap, which means that if I give you the residual, and if I give you the mu estimate, then you can give me quite easily the corresponding incremental claim, the corresponding x. Yeah, that's the idea. Now, if you look at this Poisson model, there's one additional parameter that we didn't discuss extensively, and that's this dispersion parameter, this phi. Yeah. And if you look at this dispersion parameter phi, if we look into the literature of generalized linear models, then we'll see that one way to estimate this phi is with the Pearson chi-square statistic. So then we're going to take the Pearson residuals, square them, sum them over all the cells in the upper triangle, and divide them by n minus p, where n would be the number of observations. That is the number of cells in the upper triangle, and the p would be the number of parameters used. Yeah. So that would in this case be how many alphas and how many betas do you need to estimate. So the essential thing here is I've got this dispersion parameter, I can work with this. Okay, so that's a given. And we're now ready to set up our bootstrap procedure. And yeah, a small tweak that is often discussed in the literature on this bootstrapping with the Pearson residuals is that we can also go for a just formula that we introduced earlier on. That's this guy. So if I have a residual and if I couple it with the fitted value for this particular cell ij, then using this formula over here, I can get a corresponding incremental claim amount xij. So the only thing I do is I shuffle these residuals around. Yeah. And Pearson residuals, and these adjusted Pearson residuals, we get them from the original Pearson residuals with a small tweak. So what we're going to do here is we're going to say with a prime, that's my square root n divided by n minus p times the original Pearson residual. So I can do this again for any cell in the upper triangle. Why do I call them bias adjusted? Because if I now look at the dispersion parameter, once again, so look again at my dispersion parameter phi. In the phi hat from the previous sheet, I was dividing by n minus p, and that's a bias correction, right? But if I look at this phi hat, I can now write this as the sum of the adjusted Pearson residuals squared divided by n. So I no longer need the bias correction. I no longer need to divide by n minus p. I can just divide by n because I'm using here these adjusted residuals. If you work this out, you would get the sum, and then you have n divided by n minus p, the original squared residuals, and you're going to divide by n, so that reduces to our original proposal for the estimate or the estimator of our Pearson, of our dispersion parameter, right? So that's why we call them bias-corrected Pearson residuals, because if I now use these adjusted Pearson residuals, I no longer need the bias correction when estimating the dispersion parameter. I no longer need to divide by n minus p. I can just divide by n. Good. Relying on the... That's what... So now we're ready to put this bootstrap procedure together. And we're going to start, let's say, with a step 0, which is an initialization step. So we're going to start with the incremental claims, say x or xij, in the upper triangle. And having this upper triangle available, we can get the adjusted Pearson residuals Yeah, we put them in a green triangle called RP prime, the adjusted Pearson residuals. And we can also get from our over-dispersed Poisson model, we get our mu heads. Yeah, so these are my adjusted residuals. And in blue, I've got my fitted values. And do recall the way how I put these together is by using this over-dispersed Poisson model, by estimating the parameters alpha and beta, and calculating these residuals, calculating the fitted values for each cell in the upper triangle. Now what I'm going to do is I want to create new artificial runoff triangles. So I want to get sort of artificial copies, if you want, that can replace this black triangle, and on which I can repeat the estimation of my over-dispersed Poisson model. And the way how I'm going to do that is I'm going to resample my residuals. Yeah. So I'm going to shuffle these residuals around. So I'll get a new, let's put it again in green. So I'm going to shuffle my residuals around, and I'm going to get a new triangle with the shuffled residuals. And this shuffling, that's done with replacement. Yeah, so it essentially means that I put all my residuals into a basket, let's say, and then for each cell in the upper triangle, I'm going to pick a residual from this basket, and I'm going to use it as the residual for that particular cell, and I'm going to do this experiment with replacement. So I can shuffle these residuals around because I assume that these are independent and follow the same distribution. Now I'm going to use this triangle by combining it with my blue triangle. So create a replicating triangle, or a bootstrap triangle if you want. So in order to do that, I'm going to use my green shuffled triangle with the residuals, and I'm going to combine it with my mu heads, where for each cell I still have my fitted value as I originally obtained it. I don't do anything with that. And I'm going to combine these two into a new triangle, say X star. And the way how I can do that is by yet over here I've got a new triangle, that's my X star. Now if I have a new triangle, I can fit my original model on this triangle. So that's the idea. You create a new copy, you create an artificial triangle over here, that's the X star. How do you do that? From the original triangle, you construct the triangle with the residuals, you construct the triangle with the fitted values, you shuffle the residuals around, you combine the shuffled residuals with the original estimates for the mean of your incremental cells. Put these together, you get an artificial triangle, X star. Then that's the next step. We're going to go to step 3. We take the new triangle, X star, and we calibrate our ODP with Poisson, with the chain ladder structure for the mean, which means with a structure exponential of alpha I plus beta j as the mean, right? So what I get here are new parameters, say alpha star and beta star. Because you started from another triangle, you repeat the estimation of the ODP model, you get new parameter estimates. And with these new parameter estimates, I also get a new point estimate for my triangle, for my lower triangle. I won't denote them with a head because they're estimates. So with these new parameter estimates, I get a new estimate for my lower triangle, so for the future. And that is here denoted with mu star in the future. So I get a point estimate for each cell in this lower triangle. And these mu stars for the lower triangle, they are of course different from the mu heads that I obtained initially, because I did this whole reshuffling with the residuals, and I created an artificial copy of my upper triangle. Yeah. So what we've done up to this point, and that's important, we took the parameter estimation error into account. Essentially because we obtained new parameter estimates, alpha het star, beta het star, and we constructed the point estimate for the lower cells in the for the cells in the lower triangle. We constructed them using these new parameter estimates. So up to this point, we constructed an estimate for our outstanding reserve, or for every cell in the lower triangle, taking the parameter estimation error into account. Now in the last step, what we're going to do is we're going to add so-called process error. And the way how we can add process error is by moving from this mu het star, which is a point estimate for the expected amount corresponding to a cell in the lower triangle, by taking it from there and by adding my ODP error. Yeah. And here you have to think how to do this, how to generate a draw from an over-dispersed Poisson distribution. But if and I'm going to explain that right away, but if you're able to do that, you now get values for the cells in the lower triangle, which take both the process and the parameter estimation error into account. And of course, you can now get a value, a simulated value for each cell in the lower triangle, taking parameter estimation error, process error into account. You can add these together and you get a simulated value for the total outstanding amount that corresponds to the lower triangle. And then the whole idea is if you repeat this recipe, if you repeat that 1,000 times or 10,000 times, then you get a predictive distribution for the outstanding claim amount, a distribution that takes both the parameter estimation error and the process error into account. So there is one last step use here in the final step, where I say, okay, you've got your estimates for the mu, for the mean. You want to add process error, so you want to make a draw from a model, from an over-dispersed Poisson model, which has the mu het star here as the mean. So then you're going to apply the recipe that we just discussed. Say, okay, I've got a new triangle. I can repeat my model fitting procedure on this triangle. I get new parameter estimates. If I have parameter estimates, I can put them together and get estimates for the mean in my over-dispersed Poisson model. So that's my mu het star. And then there is one last step to do, and that is how to go from the mean of your over-dispersed Poisson model to an actual simulation from this over-dispersed Poisson model. That's what we do to cover. And that is, if you say X is from an ODP with mean mu and a dispersion parameter phi, then how can you generate such? Then how can you generate a value from this distribution X? So what we're going to do is we're going to define X as phi times Z, and we're going to specify Z as from a Poisson distribution with a parameter mu, because then we know that the expected value of X is phi times the expected value of Z. And here I need to divide by the dispersion parameter. So that's going to be phi times mu divided by phi. So that's the mu that we want to have. And then the variance of X is phi squared times the variance of Z. So that's going to be phi squared times mu divided by phi. So that's phi times mu, as it should be. So here you've got your recipe. If you need to make a draw from an over-dispersed Poisson model, then you can make a draw from a regular Poisson model with as the mean the the mean that you want to achieve, so the mu that we have over here, you divide it by the dispersion parameter. So you pick a draw for the z, you multiply it with phi, and that's going to be your simulated value for x from the over-dispersed Poisson model. So that's what I would